Okie dokie, chemists, let's get this party started. So just a couple announcements before we jump back into chapter 5. Just some important exam related things. So this is our last lecture before our first midterm exam on Tuesday in class. So we'll just be replacing, typical lecture time with instead taking an exam instead. So it's important that you, one, arrive on time. Our exam is 70 minutes long, or that's how much time you'll be given as that Carmen exam. And our class time is 80 minutes long, and that's when we'll close it. So basically, there's only about 10 minutes of kind of leeway time. So if you arrive late or you can't get into the exam or something like that, we won't be extending that time. So make sure that you do arrive on time and are prepared to take the exam at 2:20. Make sure you bring, one, your device with Lockdown Browser tested. So you probably have seen that all of the practice material is behind Lockdown Browser because I think it's really that important. I want to make sure everyone's devices is set up for this exam. We also have a test quiz that you can test it out with, but make sure that you know how to use Lockdown Browser because that is what our exam will be behind. Make sure you have a photo ID. This can be a Buck ID, a driver's license. It can even be a passport or something. We just need to be able to prove your identity when we hand out scratch paper. Make sure you have your approved calculator. So that's the TI series, not the TI Nspire, not the TI 89, and no Casio calculators. There is an onboard calculator in Lockdown Browser. It's just not very user-friendly to use. And then finally, a pen or pencil, because we will be providing you scratch paper with the supplemental information and the periodic table, all that stuff. I already posted that information on the midterm preparations page. So that's next Tuesday. And so in preparation for that midterm, I will be holding an optional review session on Monday evening in this room. So at what did I write? 5:30 to 7:30. So drop in if you, you don't have to stay the whole time. You don't even have to arrive on time. It's very informal because it's optional. It's in this room. You can also attend via Zoom. And I'll also record the session as well and post it on that page. So I have this as a calendar event on our course. That's where you'll find that information. All right, so that's about the exam. Some other little things. If you have your lab review tomorrow, the midterm exam review in lab, make sure you bring your calculator. It'll just make the session more useful to you if you have the calculator that you plan to use at the exam, because I have lots of practice questions for you. How was the review? Was the review good? Was it useful? Yes, okay, all right. No fist fights? None that I saw, all right. So bring that calculator to the lab review. It'll be very useful in preparation for this upcoming exam. A note about portfolio, you'll learn a little bit more about that at the review session as well. It's kind of like the second half of that class period. That is due the night of midterm 1. So I actually moved the due date a little bit. Instead of having it due before midterm 1, I'm going to have it due just that same night, so no one's scrambling to get it done before the exam. And I also have a 24-hour grace period after that. So, but then that grace period's gone. So make sure that you upload your sample calculations to that assignment right at that midterm. All right, and then finally, who has to do that GE interview assignment? Yeah. All right, so I teach hundreds and hundreds of students every semester, so I get a lot of requests for this assignment. And after the first time I did it, I realized that all of you asked the same questions, the same 5 questions. So I scheduled a dozen interviews for no reason because it was all the same questions. So instead, what I do to accommodate all students who have that assignment is that I just do a group session open to anyone. So this will be in McPherson, 1041. It'll be on Zoom. I'll also record it. I'll do this group session basically after midterm 1 for your class and another class of mine. I just do this group session so we can get the 5 stupid questions out of the way, and then you can ask me actually interesting questions. But yeah, I'll do this Tuesday after my office hours, so at 4:30 in McPherson 1041. If you have no idea what I'm talking about, just ignore everything I'm saying. But if you do know what I'm talking about, There's a group session here. It's on Zoom. I'll record it as well. Let's worry about it after the midterm exam, though. Good? All right. Any questions about the exam? Anything? Questions? Okay, so we're going to move on and continue Chapter 5, gases. I do want to remind you that midterm 1 is only chapters 1 through 4, so 5 will not be on this exam. Okay. All right, so we left off right here talking about ways that we can measure gases. We already talked about pressure, force over an area and those units, how to convert them, volume. We can talk about volumes of gases. We're going to use liters and milliliters, so I have a note here. Might as well just memorize this equality, how liters and milliliters are related to one another for quick conversions. We'll also bring back the notion of moles, where we can measure the mole amount of gas. That'll be important when we start doing some calculations. And then finally, temperature of our samples. Typically in lab, we use thermometers that are measured in Celsius, but when using these gas law equations, we need to convert that Celsius temperature to Kelvin. So this equation allows us to convert between Kelvin and Celsius, where our Kelvin temperatures are our Celsius temperatures, but you add 273 within there. So you can have negative Celsius values, but you cannot have negative Kelvin values, because absolute zero means absolute zero is 0 Kelvin, where basically molecular motion ceases to exist anymore. All right. So so do make sure we do a little bit of reading comprehension of what units are given to make sure that our equations work out that way. And then I mentioned that, sometimes scientists, chemists were lazy and we don't want to restate the conditions every single time we describe a sample. So we can be lazy and use the terms STP to mean standard temperature and pressure. And so what standard means in this case is 0 degrees Celsius or 273 Kelvin and 1 atmosphere of pressure. So notice that standard is very earthly conditions. 1 atmosphere is what our pressure is on Earth, and 0 degrees Celsius is the freezing point of water. So that's what we considered standard temperature and pressure. We can talk about gases at those conditions or other conditions. This is just kind of like a shortcut for us. All right, so I'll do some demos now, where we will look and see how are some of these properties related to one another. So what we're going to talk about are the 3 different named gas laws that relate to pressure, volume, and temperature. So in all of these gas laws, we are fixing the amount of sample that we have, and we're just changing the environment that that sample's in. All right, so yeah, we're observing how the same sample in just different either temperature, pressure, or volume conditions. Okay, those are my announcements. Okay, so let's look at the first law here, Boyle's law. The name is really unimportant. What I care about more is that you understand the relationship between the actual measurements. So notice here, this is what Boyle's law states. At a constant temperature, the volume of a gas varies inversely with the pressure exerted on it. So we can kind of, summarize this as at a constant temperature. So like right now it's a constant temperature. It's like staying at room temperature. If you increase the external pressure on your sample, our volume of our sample changes how? It's going to decrease, all right? So we're gonna apply a pressure on our sample, that volume gets smaller. Or if we take away the external pressure on our sample, then the volume increases. So, we can rewrite it as a relationship this way as well. Volume is proportional to the inverse of pressure. That fish means proportional to, just so you know. And of course, this is when N is constant, meaning that your sample is not changing, you're just putting it in different environments. We can also use this equation to make that relationship with actual values. P1, V1 equals P2 times V2, where the 1s and 2s are basically, this is like condition 1, and then these are the values for condition 2. All right. When using this equation, just make sure your pressure and volume units match. All right, so let's do this demonstration. I've never used this vacuum pump, so I hope I do it correctly. All right, so we're going to look at at Boyle's law, so how pressure and volume are related to one another. So I have to do a little bit of background information here. So what I have here is a marshmallow snowman. Has anyone ever made a marshmallow or seen how a marshmallow is made? Ooh, very good, at least a couple people. So I'll just give you the gist of how you make a marshmallow. You take sugar, you melt it, so make it molten, all right, and liquidy, add some gelatin, and then you take a whisk and you beat the crap out of it, all right? So what's the purpose of beating that molten sugar with a whisk? What's the point? Add air, yes. So I just wanted to, emphasize that this marshmallow is made up of a ton of little air bubbles. Air bubbles, each of them has like a specific volume. So he's living in a bell jar right now because I'm going to turn on this vacuum pump, which will literally suck out all of the air that's just inside this container. Because right now, this marshmallow man, what's the external pressure that's on him right now? 1 atmosphere, because he lives on Earth with us. So what I'm going to do is just simulate, okay, let's remove all the pressure, but just inside this vacuum, or just inside this bell jar, and predict what's going to happen to that really, those fluffy marshmallows, what's going to happen to that volume. So what do we think? When I turn on this vacuum pump, how's his volume going to change? I'm getting rid of the pressure inside here. So think about how it's going to change. Oh, I wanted to put on the camera thing. Let's get it on camera. Okay, see Marshmallow Man? There we go. All right. Okay, so let's see. All right. Okay. They told me this will go really fast. Usually we use a weaker vacuum. Okay. I hope this works. Oop. There we go. So how's he changing? His volume is increasing because we're reducing the pressure on him. All right, great, great. Yeah, so that kind of went really fast. Okay. Okay, there we go. So yeah, he got really big because we reduced that pressure. And so something else that I can do here as well is open up this flask, because right now there's a vacuum inside here. So if I open up this stopper thing, it should, okay. Oh yeah, so I crushed him. So did you hear that sound though? Yeah, what's that sound that you were hearing? Air, all the air rushing where? Back into the bell jar, and that air rushing back in crushed him. All right, so yeah, so goodbye, Marshmallow Man. All right, good. And cool, I got it on a video now. All right, so that is Boyle's law. Again, the name isn't super important. I just want us to know the relationship between pressure and volume at a constant temperature. So I guess we didn't measure it. Did our temperature here stay constant the whole time? It did, because we stayed at room temperature. All right. Okay, so that is Boyle's law. So now let's look at Charles' law. So notice here, it says, at a fixed pressure, the volume of a gas is proportional to its Kelvin temperature. So at a fixed pressure, meaning pressure is staying constant. So at constant pressure, this is typical like bench work, because in lab we are doing lab experiments on Earth, and what is the pressure on Earth? 1 atmosphere. Does it stay 1 atmosphere all the time, basically? Yes, it does. So if I do a benchtop experiment up here, it's basically staying at constant pressure. So what I'm going to do here is do an experiment where I vary our temperature and see how does that affect our volume. But again, we're fixing our pressure. We're not using our vacuum pump here in this example. So here we see volume proportional to temperature, or we can say at a constant pressure, as temperature increases, the volume of your sample will increase. So let's look at this demo. I don't need to do a video for this one. All right, so right now, this balloon, this is condition 1. Oh, they probably want me to wear gloves. Right now, we're in condition 1, meaning like earthly temperatures. It's 1 atmosphere right now. It's room temperature. So what I'm going to do is pour some liquid nitrogen on this balloon. Liquid nitrogen is very, very cold. All right, very cold. So right now this balloon is, pretty warm. It's room temperature. So if I pour this liquid nitrogen on it, what do you think is going to happen? Balloon's going to shrink, yes, because temperature and volume are proportional to one another. So we should see it shrink. Come on. Oop. Go. There we go. So there we go. Our balloon's all shrunken. See, looks all shrunken. It looks like there's no gas in it at all. When we do this demonstration in front of children, children are not very smart, okay? And so when they see this, they go, oh, all the gas went away. But did the gas go away? No, that gas is still inside this balloon. It's just really, really cold, so therefore its volume's really small. So what would happen if I take this balloon out and just start warming it up again? It'll just go back to where it was, back to condition 1. It'll expand. Warming it up now gives those particles more kinetic energy, and it's going to go back to exactly what it was before. But again, children aren't very smart. So they think it's like magic. They're like, oh, you're pulling the gas in and out on their own. But no, it's just the idea of reducing the temperature or overall kinetic energy of the particles inside there makes the volume of that balloon either larger or smaller. So there is Charles' law. I like Charles' law too because something kind of special comes from Charles' law as well. The idea that if you cool something, a gas sample enough, theoretically, there's a point where you can cool it down to a certain point where your gas sample has zero volume. So regardless of what sample you're looking at, so this I'm just kind of graphing that trend, volume and temperature proportional, so you can reduce the temperature, reduce your volume. Right here at this point, I have 4 different samples that I tracked, and you see that all of them reach a 0 volume, so 0 liters, when temperature is 0 Kelvin. So basically, Charles' law kind of proves the existence of a 0 Kelvin, where our particles are no longer moving and our gas samples completely condense to take up zero volume. So that's where you would. That's kind of how you theoretically get what absolute zero is, negative 273 Celsius or 0 Kelvin. But do remember that this temperature pressure relationship is when temperature is in Kelvin, not when it's in Celsius. All right. Okay, so then the last named gas law, this one's kind of similar to Charles' law, actually. So, but this one has another name. So Gay-Lussac's law states that pressure and temperature are proportional to one another when your volume is constant. So this means like in a rigid container. So in a rigid container, your volume's staying constant. So this equation is saying as temperature increases, pressure increases. And again, here is an equation to show that. Unfortunately, I don't have a demonstration to show this, so instead I'll use an example from my childhood. My core memories is an episode of The Simpsons where Homer, I think Apu comes to visit Homer to get some parenting advice, and Homer is making dinner for his family, and he puts closed cans of beans on the grill. And we laugh because when you hear that or you imagine that, heating a closed can of beans, what do you think's going to happen eventually? Yes, they'll explode. And really what that is demonstrating is Gay-Lussac's law, that in a rigid container, if you heat it up enough, the pressure will build up to the point where that container fails and explodes. And that's exactly what Apu does. He sees all of this. These cans of beans, Homer says the beans seal in the flavor, and he grabs a shield and it explodes. So that is actually demonstrating Gay-Lussac's law. Rigid container, increased temperature, pressure increases, and at some point that container is going to fail. All right, so those are 3 named gas laws. We just saw the same sample in different environments, and we saw how pressure, temperature, volume are all related. Good news is we don't have to actually memorize these laws individually. We can just combine them all into one gas law to recognize, okay, how will a sample change if I put it in condition 1 or condition 2, relating pressure, volume, and temperature. So what we're looking at here is the combined gas law, where we say, okay, pressure 1, volume 1 over T1, so that's the pressure, volume, temperature at condition 1, is equal to the same ratio, pressure, volume over temperature of condition 2. That's it. And so that applies the, proportionalities, the inverses, and stuff that we just talked about. So how we use this combined gas law, we don't need to be super special with units. We just need to make sure that our pressure units are just the same. Doesn't matter what it is, they just need to be the same. So like ATM or torr. Our volume units also need to be the same. So it can be liters or milliliters, but temperature T1 and T2 must be in Kelvin when you use this equation, all right? And so we combined all P1, V1, and T1 terms here, so pressure, volume, and temperature. But if ever you have a situation where one of those terms stays constant, so pressure, temperature, or volume, you literally just leave it out of the equation. So for example, like when we did the balloon thing here, the pressure never changed. It was 1 atmosphere in condition 1 and 1 atmosphere in condition 2. So if a variable here stays constant, we can just leave it out of the equation altogether, because if you have the same number on each side of the equation, it cancels itself out. And so that's how you get out Boyle's law. That's how you get out Charles' law from this combined gas law. Right, so you will get this equation on exams. Cool. All right, so let's practice using this equation. Right? It's all about reading comprehension, knowing what is condition 1 and what is condition 2. So here I have a problem at constant pressure of 1.6 atmospheres. We have a sample, and it occupies this volume at this temperature. What will the volume occupy at this new temperature? So notice that I, used different colors here. 8.32 liters, this is going to be a volume, but it's going to be the first volume. That first volume goes along with that temperature, so T1. We're basically saying, oh, our sample occupied 8.32 liters at this temperature, 350 degrees, so both of these get the 1 designation. I tell you the new condition, so 420 Kelvin, that's T2, and it looks like we are solving for, what is this, V2, right? So there's our volumes, there's our temperatures, so what should I do with this pressure? So you might be like, oh, okay, that's pressure, but is it P1 or P2? Yes, it's actually both. Yes, very good. So this is P1 and it's P2. So we can either put it into the equation, or do you want to just leave it out? Let's just leave it out. So we can just leave it out of that equation, right? Because if we have 1.6 on both sides, it'll just cancel out. So it looks like here we are solving for V2 in this expression. All right, so just kind of move some things around. V2 is equal to, I'm really bad at basic math, V1 times T2 over T1. Is that right? Okay, all right, good. All right, so just plug in those numbers that were given. 8.32 liters, that's V1. The new temperature, T2, 420 Kelvin, so I'm already in Kelvin, so that's very nice. How nice of me. And then T1 is 350 Kelvin. And so we see that V2, oh, I have that right there, is about 10 liters, right? And that fits with our Boyle's, or no, what is this, Charles' law here, where, okay, if we increase the temperature from 300 to 400 Kelvin, yes, our volume should go up, and that's exactly what happens here, right? And of course, V2 is in liters because V1 was in liters, all right? So those V units have to match. All right, so that is one of them. Let's look at another one. Okay, we have a sample of argon. It occupies a 2-liter flask at this pressure and this temperature. So to me, that sounds like V1, P1, and T1. So 0 degrees Celsius, might as well convert that into Kelvin, so 273 Kelvin. And here I ask you, what temperature will the gas display if we now put that same sample into a new pressure and new volume? So here is P2 and there is V2. So it seems like I am solving for a new temperature, so I am solving for T2 here, all right? Okay, so I'll just highlight what I'm looking for. I'll move around all these variables. Notice that everything's changing, but that's okay. So let's move some stuff around. T2 is equal to what? P2 V2 T1 over P1 V1, is that right? I hope so. So yeah, I just isolated T2 on one side because that's what I want to calculate. So let's go ahead and put in those numbers. Be very careful with the 1s and 2 subscripts. So notice that P1 and P2 have the same unit, ATM, so that's good. So 10 atmospheres times V2, 5 liters, times T1, 273 Kelvin, over P1, so that is 8.6 ATM times 2 liters, right? So if you solve for this, you get T2 is 793.6, but what's the unit that comes out? Kelvin, yes, very good. Kelvin, because temperature T1 is in Kelvin, so T2 has to be in Kelvin. But I ask you the Celsius temperature, so we just got to do a little bit more finagling. Subtract 273 from this to get our Celsius temperature of 520 degrees Celsius, right? All right, so in that example, everything changed. But notice in both of these samples, or these problems, we have the same sample, we're just putting it in different conditions. That's when we used the named gas laws, the combined gas laws. Same sample, just different conditions. So now let's look at the last, I guess, named gas law, and that is technically, it's called, I guess, Avogadro's law. All right, so we saw an example where, you know, temperature affects volume, pressure can affect volume. But another way we can affect volume is just think about like a simple balloon. If we had like a, you know, like a latex balloon and we used our lung air to fill up that balloon. When the balloon is small, there's not a lot of air in it. When there's, we have a big balloon, there's a lot of air particles in there. So what Avogadro said is that the number of particles, so N is just the number of moles of gas that are in your sample, is proportional to the volume, right? So again, like blowing up a balloon, how do we get more particles inside that balloon? We just blow it up with our mouth, right? So we can use Avogadro's law and actually add it to our combined gas law and get this, that, okay, all of these things, volume is dependent on pressure, temperature, and number of moles of gas sample that you have. So we have this new proportionality, and this gives us our ideal gas law that now relates how much sample you have to pressure, temperature, and volume. And so with this idea that, oh, the mole amount of sample that you have affects volume, gives us the ideal gas law, right? So this ideal gas law, PV equals nRT, or PIVNRT for short, describes one sample at one condition. Okay, combined gas law was one sample at 2 different conditions. But this one, it's one sample, so one N amount of sample at one pressure, temperature, volume condition. So PIVNRT, here we see pressure, volume, temperature, and our mole amount, right? So all of those terms are there, but then now we have this new term, R. This is our gas law constant. R will always be given to you on exams. There's actually a lot of R's out there. Right? If you Google gas law constant R, you'll find on Wikipedia a list of like a dozen different values, and they all have different units. So what I'm going to show you is one unit of R. So this one, the 0.08206 liter ATM mole Kelvin. We'll use this type of R with the understanding that in order to use the ideal gas law equation, we need to make sure our volume is in liters N is in the unit of moles, pressure is in atmospheres, temperature is in Kelvin, because these are the only units that work with this R. There are other R's that have other units, but it's easier to just memorize one unit of R and just convert everything to like atmospheres or liters. It's easier to do those conversions than like memorize a bunch of different R's. That's not like necessary. So we'll use this version of R. Just make sure that, you know, we have these units always there. All right, so let's do some example problems. Okay, so these are typical gas law, ideal gas law type calculations. Notice that it's one sample at one condition that we just want to know more about. So let's consider a 12-gram sample of helium, and we place it in a rigid container, rigid 5-liter container. The container explodes if the pressure inside exceeds 20 atmosphere. What temperature in Celsius will the cylinder explode? Do you ever have like intrusive thoughts and want to do something real stupid? Yeah, so like when you're sitting at like a campfire and think like, oh, what would happen if I threw this can of spray paint into like the campfire? Yeah, those are the intrusive thoughts I have. So that's where this question comes from. All right, let's calculate, okay, at what temperature will this, you know, spray paint can explode? All right, so here I tell you how much sample you have, 12 grams. I tell you the volume, there it is. And I tell you that the container will fail. It explodes at 20 atmospheres. So there's our pressure. And it sounds like we are trying to solve for T. So really the only thing we're missing if we want to use PivNert, all right, I give you pressure, I give you volume, I want temperature. We just need the mole amount. I give you a gram amount. So this is where I'm going to get the mole amount of helium. So we're pulling out of the depths of our brain skills from molar mass conversions from chapter 3. So those are absolutely still important here. We're going to start with the given gram amount of helium. We cannot just put 12 into PivNert right away. We have to convert it into moles, all right? Okay, so what number should I use to convert grams to moles for helium? Molar mass, and what is the molar mass? It's like 4 something. Is it 4.03? I don't know. Oh, what? 0, 0. Okay, all right, so it's 4. We're going to just say helium is 4 grams per mole. Perfect. So we're going to use that to convert to moles. So the 4 goes where? On the top or the bottom? Bottom. Okay, 4 grams of this stuff is 1 mole of helium. Oh, cool, then it's a nice even number. So that means that this helium gas container contains 3 moles of helium. This is our N amount. So when we look at PV equals nRT, now we have everything we need to calculate temperature. We are given pressure, we are given volume, we just got N, R is a constant. Go ahead and solve for temperature. So I'll just rearrange that. Temperature equals PV over nR. So now let's place all those values in. 20 atmospheres, so ATM is good there. Volume is 5 liters. N we just calculated is 3 moles of gas. And then R is a constant, 0.08206 liter ATM mole Kelvin. So if you look at the units here, atmospheres cancels, liters cancels, I've run out of colors, blue. Moles cancels, so the unit that's left here comes from R. We have a 1 over Kelvin in the denominator, so Kelvin gets kicked up top. So that means that the temperature that comes out of this is, in fact, in Kelvin. Okay, the answer is in the corner there, so 406.5 Kelvin. But, you know, we don't have thermometers that measure in Kelvin. We want to convert that to Celsius. So we'll subtract 273 and we'll get a temperature reading of 133 degrees Celsius. So that's the temperature at which our intrusive thoughts win. Okay. All right, so notice 1 sample, 1 condition. So that's when we use PivNert. So let's do another one. So we're, again, pulling out of the depths of our brain ways we were able to play with moles back in chapter 3. We had molar mass. How else did we play with moles? Avogadro's number. So if we know the mole amount of gas present, we technically also know the number of particles that we actually have. So let's calculate the number of gas particles that are present in one deep breath of air from our lungs. If I tell you that the volume of your lungs is 2.25 liters, your body temperature is 37 degrees Celsius, so what is that? 310 Kelvin. And the pressure inside our lungs is a little bit less than 1 atmosphere. It's just a 0.967 atmosphere. So that's our pressure. All right. So in this question, I give you pressure, I give you volume, I give you temperature. So I have all the information I need to get to N, mole amount of gas. But this question's asking for individual particles. So this is where we're going to use Avogadro's number. So 6.022 times 10 to the 23 particles are present in 1 mole of sample. So our strategy here, use PivNert to calculate N, and then use that N amount and Avogadro's number to get to the individual particles. So let's just go ahead and do that. Solve for N here. Move some stuff around. PV over RT. This will tell me how many moles of gas are inside my lungs. So pressure is 0.967. Volume is 2.25 liters. R 0.08206 liter ATM mole Kelvin. And then finally the temperature, again, make sure you convert that Celsius to Kelvin, 310 Kelvin. All right, so when I multiply and divide all that stuff around, what is the unit of N that comes out? Moles, yes, 0.0855 moles. Let's just check that. ATM cancels, liter cancels, Kelvin cancels, so we have a 1 over mole in the denominator, so it gets kicked up top. So yes, a mole absolutely does come out of this equation. So it's 0.0855 moles of gas, but I want to know the number of individual particles inside there. So I'm just going to take that number, recognize mole is just a counting number. It's like saying a dozen of something, which is 12. So I'm going to multiply by Avogadro's number, all right, particles, and then I get a little less than a whole moles of particles. 5 times 10 to the 22 particles are present in that one deep breath of air. So we're just, again, playing around with moles just like we did in chapter 3. It's just we have a new way to do that with PivNert, PV equals nRT. Okay, let's do a couple more applications of gas moles. How else did we play with moles? Stoichiometry. So let's do a question where we have to apply stoichiometry and the mole ratio between reactants and products. But this time, you know, in chapters 3 and 4, we measured our reactants and products with gram amounts. We measured our reactants and products with molarities and volumes. So in this chapter, chapter 5, we just have a new way to talk about how much sample we have. Now we're going to talk about the pressure, volume, and temperature of our sample to, again, figure out how much reactant or product do we have. So here's a reaction. This is what airbags are made out of, sodium azide. So it's a solid, right? So a small amount of solid is inside your airbags that is sensitive to like touch. In that, so, you know, when you are in a crash, then they explode and produce a lot of gas. So you see here in this reaction, 2 moles of sodium azide, when it reacts, makes 2 moles of sodium, but it also makes 3 moles of nitrogen gas. So what we're going to focus on is this stoichiometry. 2 moles of solid makes 3 moles of gas. We can measure how much solid we have using gram amounts and molar masses. We can measure how much gas we make with PivNert. So it's, again, just a new skill, a new toolbox, a new tool in our toolbox that we can use to do stoichiometry. So if we have 12 grams of sodium azide, that is our reactant, and we place it in an airbag at STP, what is the final volume of nitrogen after all of that sodium azide completely reacts. So our strategy here is just like in chapter 4. Take the gram amount of what's given, convert it to moles, hop on the bus, 2 to 3 ratio. Now you have a mole amount of your product. But instead of converting this mole amount to like grams, we're going to describe it as a gas and use the PV temperature information to get liters of that gas instead. So really, the only new step is this last one. That is the only new step. Everything up until here is absolutely review from chapter 4. The only new thing is we're going to take that mole amount and plug it into PivNert. So notice I didn't really give you temperature pressure information, or did I? I did. I got lazy and just said STP. So STP means what? The temperature is 0. 0 what? Degrees Celsius. So it's not 0 Kelvin. It's actually 273 Kelvin. And then the pressure is 1 atmosphere. All right. So I told you without telling you what the pressure and temperature is. So let's do this. 12 grams of sodium azide. We're going to use that molar mass. I gave it to you at 65. So 65 grams of sodium azide is present in 1 mole of sodium azide. All right, now let's ride the bus of our chemical equation, because now I'm in the unit of moles. So it's a 2 to 3 ratio. Which number goes on the bottom, the 2 or the 3? 2, right, because we are in the unit of sodium azide. So we're going to say 2 moles of sodium azide, or NaN3. 2 moles of NaN3 is equal to 3 moles of nitrogen gas, right? So we just did molar mass, stoichiometry. If this was chapter 3 or chapter 4, we would do molar mass, stoichiometry, molar mass. But we're not going to end with molar mass. We're just going to get the mole amount here. So if you do all that math, you get that this reaction should produce 0.277 moles of this nitrogen gas. It's not our answer. We want to take this mole amount. This is our N value that goes into PivNert. So we're just going to shove that mole amount somewhere else to get pressure information. So PV equals nRT. We are solving for volume. So I'll just rearrange this. Volume equals nRT over pressure, and then just go ahead and place all those numbers in. So we have 0.277 moles of gas sample times R. I'm not going to write the number out anymore. It's the same one. It's 0.08206. 273 Kelvin over the pressure 1 atmosphere. All right. And there we go. So we see that 12 grams of this stuff, of sodium azide, is enough when it completely detonates, because of that 2 to 3 ratio at this temperature and pressure, should make 6 liters of volume, hopefully enough to cushion your face upon impact. All right. So we worked with moles, worked with Avogadro's number, worked with stoichiometry. So let's kind of expand our wings a little bit and look at some other applications of the ideal gas law equation. So these are other ways we can use PivNert to calculate something. So here we can use the ideal gas law to calculate the molar mass of a pure gas. I think in the book they give an equation to calculate this, but you don't need an equation to do this. So here's the problem. I give you an unknown gas sample. I tell you that your gas sample is 0.22 grams. And that gas sample occupies a certain volume at a certain pressure and a certain temperature. And I ask you, what is the molar mass of this gas sample? So if I always use units to guide me on what I want to calculate. So if I want to calculate molar mass, just remember, what is that unit? Molar mass of this gas is equal to the gram amount of that gas over the mole amount of that gas. Do we have one of these numbers already in the question? Yeah, grams. I gave you grams already. It's right there. So we already have the numerator. So that means I'm halfway done. We just need to figure out how many moles of gas we have. How do you think we're going to do that? Probably use PivNert. Yep. All right. So the gram amount of gas is given. We're going to use PivNert and all the information given to calculate the mole amount. I gave you pressure, I gave you volume, I gave you temperature. So we're just going to use PivNert to calculate that bottom unit. So let's go ahead and do that. Again, be careful with units here because volume, is that unit of volume okay? Nah, got to change it. So this is 0.1200 liters. Is this pressure okay? No, got to change it to atmospheres. Did I write it down? It's something like 748 divided by 760, whatever number that is. And then 80 degrees Celsius, we need that in Kelvin. So that's 353 Kelvin, right? So let's calculate N. N is equal to PV over RT, right? So let's put those numbers in there. So pressure is 748 torr over 460. This will put it all into ATM. Volume is 0.1200 liters. R is our same R, 0.08206. And then times temperature, 353 Kelvin. All right, so pressure, volume, temperature, R. We get that this sample with the pressure temperature data is 0.004076 moles of gas. That's not our answer. We need to calculate our molar mass. Molar mass is grams per mole. We just calculated the mole amount, so let's apply the gram amount that was given. So we started with 0.22 grams of sample, and we used PivNert to calculate the mole amount of sample, and so we get that gas sample weighs 55 grams per mole, right? So yeah, I think the book gives like a different equation, but I don't want you to memorize equations. Really, just look at the unit of molar mass. I already gave you the gram amount. Just figure out how much moles you have there using PivNert, boom, plug it into molar mass, you're good to go, all right? So that's molar mass of a gas. I have to give you the gram amount, or you can't solve it. So let's do another one more application. What else can we learn about a gas? We can also calculate the density of any gas as long as we know the conditions. So things change their density at different temperatures. So here I have a question. What is the density of nitrogen gas at this temperature, this pressure, and then reported in grams per liter, right? So the strategy for calculating density, again, use the unit to guide you. If we want to calculate density in grams per liter, if I know the gram amount of sample that I'm working with and I know the liter amount of sample I'm working with, then I can calculate density. But we have to kind of start with some amount. So here's the strategy for calculating the density of a substance when I give you a chemical formula. That strategy is assume you have 1 mole of gas. You need to start with some amount, right? You need to figure out how much does 1 mole of gas weigh in grams. You need to figure out how much does this 1 mole of gas occupy in liters. Once you have those numbers, then the calculation is straightforward. But you need to start with some amount, and it's easiest to just start with 1 mole of gas. You can actually start with any amount. It's just easier to choose an easy number like 1, right? So our strategy here, we're going to assume we have 1 mole of nitrogen. That's what we're going to play around with. So do you know how much 1 mole of nitrogen weighs in grams? Yes, it comes from the periodic table, all right? So if we are working with 1 mole of this nitrogen gas, we're going to use the molar mass to get that number, right? So that number is going to be like 28 grams. Do we have enough information to calculate how much volume this gas occupies? As long as we know that we are working with 1 mole of gas, that is our N amount. I give you temperature, I give you pressure. That's enough information. So I have the N amount, I have T, and I have P. So that is enough information to calculate volume in this case. So I'll just show you PV equals nRT. We have pressure, we have N, we have T. So really what we're doing is using PivNert to calculate volume now. And of course, we are assuming we're starting with 1 mole of gas. So let's just go ahead and do that. Solve for volume. Okay, so volume equals nRT over pressure. So again, we made that assumption that we have 1 mole of gas. We're going to multiply by R. What is our temperature? 130 Celsius. What is that? Did I write it down? No, I didn't. 130 plus 273 is 403 Kelvin. 403 Kelvin over the pressure, so 750 over 760. This is 0.987 ATM. So that goes on the bottom here, 987 atmospheres. And so we see that 1 mole of gas at this temperature and pressure should occupy 33.5 liters, right? That's 1 mole of gas. Any gas will occupy that much. But this gas, we were trying to solve for its density. So density gram per liter. So ask yourself, how much does 1 mole of nitrogen weigh? How much does 1 mole of nitrogen gas weigh? Is it 14? It is not 14. It is actually 28 grams. Yep, 28 point something. 28 point, is it 00? Yeah, okay, perfect. All right, so I'm just seeing how much does that nitrogen N2 molecule weigh in grams. And so it's 28 grams over the volume, 33.5 liters. We got that from PivNert, so there is our density, 0.836 grams per liter. So you can calculate the density of any substance, using this strategy, as long as I give you the chemical formula, the pressure, and the temperature. All right, so you could do it for helium. You could do it for fun gases like SF6, which I was gonna do a demo maybe next week of, you know, helium is lighter than air, it's less dense than air. So when you breathe it in, what happens to your voice? It gets higher, yeah. So SF6, you could calculate the density of SF6. It's really heavy, it's a really heavy gas. It's denser than air. So what do you think would happen if you breathe SF6 in? Your voice gets lower, yes. So I forgot to order that demo. I'll do it next week. Because everyone's heard the helium one, but no one really hears the low voice one. You sound like Darth Vader when you do it. So I'll do that next week for you. All right, so those are our calculations. How do we feel about that? It's kind of like review. It's another way to just play with moles, PV equals nRT. Okay, so we're going to talk about something else here, some other calculations we can do with partial pressures of gases. All right, so up until now, all the examples we used, we were looking at pure gas samples, so like only helium, only nitrogen, only argon or whatever. But most samples we interact with on an everyday basis are actually mixtures. So like the air that you and I breathe is a mixture of many gases. It's a homogeneous mixture. It's a solution also, technically, because it's made up of nitrogen gas. Oh, that should say N2. A mistake's been in there for like 5 years. It's mostly nitrogen gas. There's 20% oxygen gas in air, a little bit of argon, and like other like pollutants, other gases in there in very, very small amounts. So yeah, the air we breathe is not just pure oxygen, it's nitrogen and oxygen. So every gas that's present in a mixture exerts its own, what we call partial pressure. So what a partial pressure is just the pressure of that gas component as if it were the only gas component present, right? So we can express partial pressures and help us understand the relative abundance of each of those gases present in a sample. And what we'll see here is that the partial pressure of your gas is proportional to how much gas is present in that sample. So, you know, if your sample is 50% gas A, then 50% of the total pressure will be the partial pressure of that substance. Or you can think, okay, the total amount of gas particles you have present is proportional to the total pressure exerted by your sample. So the idea here is that all of your partial pressures add up to your total pressure, depending on how many components that you have present. Each of those pressures you can pivnert individually, or you can pivnert them together. So the mole amount of C is proportional to the partial pressure of component C, or the partial pressure of A is proportional to the mole amount of A that is present. But you can also calculate the total pressure using the total number of moles that are present in your sample. So lots going on here, lots of different pressures, lots of different mole amounts. Thankfully, all of these are related to one another, where the fraction of each of the partial pressures is also related to the fraction of molecules that are actually there. So how we represent how much of each gas sample there is we use a term called mole fraction, which just basically gives a percentage of how much is your sample each of these different components. So how we calculate mole fraction, it looks like an X, but it's actually the Greek letter chi. So this X mole fraction for an individual component is equal to the mole amount of that component over the total number of moles of gas you have present. So it's just the fraction of the particles that are that component. So what's really cool once you know the mole fraction, so let's say your sample is 80% component A, it also means that your partial pressure for component A is 80% of your total. So it's proportional in that way. So that's what this equation is showing, that the partial pressure of your one component is equal to the mole fraction times the total pressure of your system. So lots of words. I think it's easier to just do examples. Okay, so here's an example. We put 4 atmospheres of helium gas and we charge it into a container. Charge is just a fancy word for put gas into container. And that container is 20 liters at 298 Kelvin. And then we also put 1 atmosphere of neon into the same container, right? So both, we have helium and neon in the same container. So what is the total pressure of the total pressure in the tank? What do we think? 5, yes, don't think about it too hard. It's 5. You put 4 atmospheres of one gas, 1 atmosphere of the other gas. What is the partial pressure exerted by helium? 4 atmospheres, because that's how much you put in it. And then what is the partial pressure of neon? It is going to be 1 atmosphere, because that's how much you put in it. So these partial pressures are, by definition, it's the pressure each gas exerts as if it were the only one there. So notice that these 2 partial pressures add up to that total pressure, right? So we can pivnert all of these different numbers. They'll give us different pieces of information. So let's calculate what are the mole fractions of helium and neon that are present. There's a couple ways that we can do this. The best way, I guess, to do this is figure out how many moles of helium do I have and how many moles of neon do I have. Then I can calculate, since I know the mole amount of everything, I can calculate those mole fractions. So let's go ahead and do that. We're just going to pivnert both of these numbers, these partial pressures that are given. So rearranging our PV equals nRT equation, we get that the mole amount of helium is equal to pressure, volume over RT. But let's be super specific. The mole amount of helium is equal to the partial pressure of helium. We can't use total pressure here. We have to use the pressure of helium. To calculate the mole amount of neon, which pressure do we use? The pressure of neon over volume or times volume RT, right? So that's the strategy there, that the mole amount of each component is related to its actual partial pressure. So let's go ahead and place those numbers. So pressure of helium, 4 atmospheres, volume 20 liters, R, and then temperature is 298. All right, I don't think I calculated this. 4 times 20 over 0.08, so that, 298. So there is 3.27 moles of helium present. And then we're going to just do the same thing for neon as well. The partial pressure of neon is 1 atmosphere. It's in the same container, so 20 liters over R, same temperature, 298. And so when you calculate this, you get that the mole amount of neon is 0.82 moles of neon. So those two values together will give us our total mole amount. So what is that? Our total mole amount is 3.27. Wait, hold on. 0.8178 plus 3.27. There we go. Is equal to 4.1 moles total. All right. So if we want to get those mole fractions, the mole fraction of helium is going to be the helium number over the total number. So you can do 3.27 moles of helium are present in a total amount of 4.1. The mole amount of neon is just the rest of it. So 0.82 moles of neon over 4.1 moles total. And so what we get should be a very even number, 3.27, boom. So for helium, our mole fraction is 0.8, and our neon sample is 0.2. So 20% neon, 20% helium by using those mole amounts. Do we see that ratio anywhere else as well? The pressures, yes. So we actually did it the long way. We did it the long way. So what I wanted to show you was that notice that the mole amounts are in the 80-20% ratio, but if you also look at the pressures here, I did this on purpose. The mole fraction of helium is also proportional to 4 atmospheres over the total 5 atmospheres. It's the exact same number. So we can look at the relative amounts of pressures or the relative amount of moles that are present to get us mole fraction, right? So I think that gets us our entire, thing. So yeah, the mole fractions of helium and neon, and then the total number of moles of gas present in the tank. We calculated all of those things. All right. So that's how partial pressures, mole amounts, they're related to mole fraction. So let's do a conceptual one. I like conceptual questions because they do very well on exams. They separate students very well of who understands the concepts and who doesn't. So I just wrote the exam. Over half of the questions are conceptual based, meaning like you don't have to really do any calculator stuff, all right? Yeah, so it's not all calculator based, you know, it's conceptual. So keep that in mind. And I will point out that, you know, the review session that I do on Monday? So I'm holding the review session, and I write the exam. Yeah, so you should go to the review session, right? Because oftentimes I write the exam and then I write the review packet. Because if you notice, if you go to the review session information, I don't have the packet posted because I haven't written it yet. Okay, but I just finished the exam yesterday. Okay, anyway, so here's a conceptual question. All right, here's our gas sample. It's made up of red and yellow balls. Which gas sample is present in the larger mole fraction? So just looking at this picture, you know, let's just use the number of balls as the relative amount of each of those gases. So can you count for me how many red balls are there? 4, and yellow? 6. So just based upon those numbers, what mole fraction is larger, red or yellow? Yellow. Can you give me the actual amounts? The mole fraction of yellow is 6 over 10, so 60%. And then the mole fraction of red is 4 over 10, so this is 40%. all right? Okay, so then what gas exerts more pressure then? Yellow, yes, but I didn't tell you a pressure, but I didn't have to. I don't have to because we can just tell by the number of particles that are there, by the mole fractions, that the yellow partial pressure will be larger. Okay, so then if I tell you the total pressure of the container is 2 atmospheres, what is the partial pressure for each? So notice now I finally gave you a total pressure. And so we already have the mole fractions. So red partial pressure is simply going to be 40% of the total. And then yellow partial pressure is going to be 60% of the total, so 2 atm. Right? So what is that? 0.8 atm and 1.2 atm for those two gases. Right? And then finally, here's a different situation. What if I tell you instead, okay, it's the same sample, but what if I told you the partial pressure of the red sample is 1.2 atm? Then what is the total pressure of the entire container? Well, this partial pressure can go into this equation where I give you the partial pressure of red. We're trying to solve for the partial pressure, the total pressure, but I already know that the mole fraction of red particles is 40%. So we just need to scale it up. That I know if 40% of my sample is red and it exerts 1.2 atm, then the total pressure is going to be slightly higher than that to make up that full 100%. So mathematically, how I would solve this is that the total pressure is equal to the partial pressure of the red over the mole fraction of the red that is there. So this would be 1.2 atmospheres over 40% of my sample, and so you get 3 atmospheres there for your total pressure. You can also work backwards and see, oh, 3 atmospheres, 40% of that is 1.2 atmospheres, which would give you the partial pressure of that sample, of the red sample, 1.2, that is given. So this one's definitely more conceptual because there's very little math involved. It's all about really understanding what are partial pressures, how are they related to total pressure and mole fraction, right? Very little math. Okay. All right. So we got about 15 minutes left, so I'll talk about, actually, you know what? I'm gonna just stop right here. All right. So I will give you the 15 minutes to, I guess, start studying for midterm 1. All right. So we'll stop right there. Yeah. I'll still have office hours in my office today if you want to stick around, and we can go to office hours.